Thanks for joining us today for this presentation by Greg Livingston. This is Toronto STLE section. The subject of this talk is about the use of an oil-soluble cleaner to prolong long-term deposit control in rotating equipment applications. Please mute yourself. We are going to record this presentation, and after that, I'm going to upload it into the STLE YouTube channel and STLE website. You can keep your questions for end of this presentation or type them in the chat box. The chat box is on the top in the middle of the page almost. So you can type your questions there and I read them to Greg, or Greg can read it at the end if he wish himself. So a little bit about Greg. Greg Livingston serves as the Chief Innovation Officer at FluidTech with 3 decades of expertise in rotating equipment lubrication. He is a renowned subject matter expert specializing in lubricant degradation and failure risk mitigation. Greg has developed oil analysis tests and patented oil treatment technology that enhance the lifespan and performance of industrial lubricants. He actively contributes to industry organizations such as STLE, ICML, and ASTM. He has authored over 100 technical papers. Recently, Greg published a book titled Turbomachinery Cholesterol, The Story of Varnish. So, Greg, please go ahead and start your presentation. Thank you.
Wonderful. Thank you. Really appreciate the invitation, and happy to talk about one of my favorite subjects today. But in particular, we're looking at an oil-soluble cleaner that we've had some success in rotating equipment. So my outline today, I want to give you a little story of the inspiration of this technology, give you a little background on varnish and basically how soluble enhancers can be used for conversion enablers, troubleshooting, life extension, as a couple different key value propositions. So first, let me just start off by saying that we regularly do these events that we call lubrication academies, or a 1 or 2 day deep dive into rotating equipment lubrication. And so in 2009, we were in Atlanta, and I was really excited because Jim Hannon, who is I think one of the most knowledgeable people I've ever met in the turbine oil space, agreed to present at our event. And so he was presenting and going through about flushing, and came up to a slide and was talking about all of the ramifications of using detergent-based cleaners. Now, and using detergent-based system cleaners have been around for decades. This is how we clean varnish out of systems, out of turbines. If you have varnish, you do a chemical flush, you use a detergent dispersant, and the data that he showed is that even less than 0.1% of residual fluid, so you have to do a sacrificial rinse after you use a detergent system cleaner. Even after doing a sacrificial rinse, if you have less than 0.1%, it could actually impact the demulsibility characteristics of the new oil. So I was watching his presentation. I always learn things from him, and I thought, I said to my colleague, why are we using an incompatible cleaner in this case? Shouldn't we be trying to use a compatible cleaner? So anyway, that was the the big aha moment that we thought, well, maybe there's an opportunity to improve this process here a little bit. And it's kind of come full circle. So then in 2021, we partnered with Mobil and launched a product called Mobil Solvencer, which is an oil-soluble cleaner and completely compatible with the in-service oil. So it's a little background, kind of the inspiration of coming up with maybe a new way of cleaning out systems. So first, I want to do just a step back in time a little bit and do a little bit of background on varnish and take a look, maybe a historical perspective on this, and talk a little bit about some of the principles of varnish. But if we in fact look at the 1900s, in general, we actually had a pretty easy century in terms of turbine oil lubrication. It was pretty easy. So these are some of the papers that I've amassed over the years. But there was GE produced a paper in the 70s that they noticed deposits. And a relationship with deposits when you have elevated acid number and viscosity. They solved this by doing an oil change. Wilson with Chevron, he identified one. So there's a few. In 1981, there was a paper that said most turbine oils had really minor degradation, and so we did not see a lot of issues for a good solid century. And then things changed, and so now, in fact, we've had several things that have kind of happened over the first couple decades of this century. So one of the things that happened is that turbine oils evolved. So we started using different base stocks and different additive systems. And I'm going to talk a little bit more about that. Just a teaser on this. Varnish is not because of the switch to Group 2 base oils. So I just throw that out there. I still hear that. I still hear people say that. But there were new, coincidentally, there were new formulations that came in the market and new additives that require different monitoring technologies. Simultaneously, we saw really a widespread use of gas turbines that had both new sensitive controls and an integrated hydraulic control system. That was problematic. And from my personal perspective, the first big aha moment that I saw in the industry was at a large frame gas turbine user group in 2004, where basically the OEM was just inundated of complaints about valve sticking issues and all of these funky deposits that are showing up on bearings. But at the time, if you can go back 20 years, there was no varnish test. There was no way to predict this. So we actually saw wonderful, perfect oil analysis reports, no change in acid number, particle counts were low, nothing that would indicate any kind of varnish problem. And in fact, we started seeing a whole host of different varnish issues. So in 2005, the first varnish potential test was commercialized. This was started, I started in ASTM to convert this into what is now D7843. It took a good solid 6 years before that was published, but now there is the membrane patch colorimetry test. But just think back in the day, we actually had no test to really predict this happening. So we do have a new test now. Then you can see this is from my perspective. I do think this was a kind of a big thing in the varnish timeline. We introduced a resin-based filtration system and solubility enhancers shortly thereafter in 2011, 2012. Simultaneously, we also saw a whole new range of next generation turbine oils that are introduced that are producing both long life and low deposits. And today, I think we have a much better handle of varnish. We're still learning some things, but we have a pretty good sense on how to go about avoiding it. So that's high level overview or kind of historical perspective on varnish over the years. And essentially, just to make sure we're all on the same page, what do we mean by varnish? We consider this an oil-derived deposit. There are literally dozens of different chemistries that can make up varnish, depending on the operational conditions of the machine and the equipment, like the thermal stresses that the oil is seeing, formulation of the fluid, and then what other contaminants that are ingressing into the fluid that can cause multiple different degradation pathways. So some of the common varnish problems we see in rotating equipment, and this is just a high-level overview, but one of the most sensitive things that we saw, certainly in the world of gas turbines, is sticking valves, especially on systems that had an integrated hydraulic and turbine oil reservoir, sticky valves, especially the inlet guide vane valve in peaking or cycling turbines, a little bit of sticking there, we would see a pretty significant we could see a failed to trip or a failed to start or an actual full unit trip. Um, Increased wear and higher temperatures on bearings was another phenomenon that we saw. Hydrogen seal failure, and also varnish is as a polymer. It's a wonderful insulator. Unfortunately, if you coat heat exchangers with varnish, now you're going to significantly lose the efficiency of heat exchangers. So those are some of the varnish problems that we see. And if we want to take a look from a very simplistic point of view, I know that we have chemists that are watching. So keep in mind, this is not to actually, this is to represent a hydrocarbon molecule. This is actually not a real hydrocarbon molecule. But if you can just bear with me on this illustration here, just, if we looked at actually what happens in the formation of varnish, we have one of the atoms that's attacked by heat and oxygen. And this in and of itself actually is really not that big of an issue. And even once all of these things start to multiply and we have all of these degraded hydrocarbon molecules, even at this point, we're still talking about a very, very small percentage of the oil that is actually these degraded molecules. But here is the problem. These also become polar. And the challenge now is that these polar things like to agglomerate together. And now this is when we start to have some challenges. Once these things agglomerate together, the polar heads are attracted, they become larger, both in physical size and more polar, and then they will multiply, and you'll have these once you have these agglomerates in the oil, then they like to settle out and form varnish. So in a very, very simplistic way, this is one of the formation or mechanisms that we see with varnish. So that's high level overview of varnish. And now we'll talk a little bit about a product called Mobile Solvencer. I'll give you just a quick introduction here to kind of what Mobile Solvencer is. Again, it's an oil soluble cleaner, and it's a Group 5 base stock. So we're using a Group 5 base stock. There's no actual additives in here. So there's nothing that actually will deplete over time. And it's used as a solubilizing agent, which dissolves deposits and varnish back into the lubricant oil, and allowing the system to maintain to be clean. And it's also it's benign when it comes to seals and coatings and paints as well. So it doesn't have any adverse effects to the actual system, and it doesn't have any adverse effects to the actual oil. So it doesn't adversely impact additive functionality. Of course, anytime you add anything to a new oil or to an in-service oil, a lot of upfront testing is required. But this has no impact on antioxidants and antiwear or EEP additives. It doesn't cause, unlike like surface active chemistries that can cause additive fallout, or maybe the transfer of deposits from the reservoir to the IGV valve. It doesn't have any surface active chemistries, and therefore also doesn't have an impact on the lubricant's ability to manage contaminants. And contaminants, we primarily mean in the world of turbine oils, two of the biggest contaminants that we have to deal with are water and air. So it doesn't impact emulsibility, for example, or on the air side, the oil-air interface foam or air release. So that's a little bit about Mobile Solvencer. It's typically added at a rate of 3 to 5%. You add it to the actual in-service system, and it works not quickly. It works in a very slow, methodical way of dissolving kind of one layer at a time. So that's how it actually will clean up the oil system. So if we look at the primary uses of this technology, there's three different things that I'll touch on. So one is a conversion enabler, another is troubleshooting, and the third one is life extension. So in terms of a conversion enabler, this is essentially a less expensive way of doing a chemical flush to decontaminate the lube oil system in between oil changes. And so in this case, we typically would add 5% of the chemistry at least a month prior to an oil change. We prefer actually more than a month. And one of the big benefits is that during the outage, essentially, we always encourage people to do oil changes at the very beginning of the outage while the oil's nice and hot and everything's dissolved in the oil. So same thing with this. We encourage users at the very beginning of the outage, drain the oil with the degradation products with it, and no sacrificial displacement flush is needed. So it does speed up the time a little bit here as well. So if we actually go back to our little diagram here and look at actually how this chemistry is working. Here we have our degraded oil molecule. Now let's just pretend this is our solvencer molecule. And again, just for illustration purposes, well, the solvencer molecule will actually interact and combine with the polar head or the polar atom on the degraded oil molecule. And what this does is essentially now this molecule is no longer polar. So the big thing is that it prevents all of these particles from agglomerating and keeps these things very safely in the oil. And so if we actually add this to a varnish system, it's the same thing. We have this chemistry is attracted to the polar head of the varnish that is actually has settled out in the system. And then over time, kind of one layer at a time, it will dissolve the varnish back into the oil, and then all of these little degraded hydrocarbon molecules with polar heads. We have an attraction with a solvencer molecule, and it prevents these from becoming polarized and then plating out further, causing further deposits. So again, very simplistic view, but this is essentially how the technology works. So until essentially the deposits have been dissolved. So this is I just have a couple quick case studies, but this is a plant that wanted to do an oil change, had severe time restrictions, a very short outage. So in lieu of doing a varnish flush, they put mobile solvencer in 5%, and a month prior to the oil change, during the oil change, essentially drained the system, and we calculated about $104,000 of savings. Plus, there was about 3 days shaved off their outage resources. We've seen the same thing. Also, this is in a paper mill that we saw kind of a similar thing, but we have this is one really solid use case for using solubility enhancers like this. All right, the second use case is in the world of troubleshooting. So we've talked about conversion enabler, troubleshooting. Now, we gave a nice, I showed you a very simple example of how deposits form, basically by these polar heads agglomerating together, reaching kind of the saturation point of the oil, coming out of solution, and then forming these deposits. There are other mechanisms of varnish formation, and that is typically if you see heavy varnish on bearings, on the journal bearings or on thrust bearings, we typically have another mechanism at play. And so this has been something that we have been studying a fair bit, but in what we tried, we are trying to create a mathematical model that will predict when the formation of what we refer to as shear stress deposits actually happen. So this is some of the formulations we've used. If you're interested in this, there's a Tribology International. We have a paper about this that goes into, well, especially if you love math, it goes into some deep math that's way, way over my head. But we have developed a way to map the temperature of the bearing, and basically predict where the highest temperature is going to be. Essentially, it is the highest load, the minimum oil film thickness, and the whole concept of shear stress deposits is that we have, based on rotational speed and heavy load, we basically have so much temperature happening in the minimum oil film thickness that it causes the oil to internally cause internal shearing and create very high temperatures just within that small oil film. Um, so this is an issue that we see, with we don't see group one so much anymore, but group two, group three, even group four oils, we still see this phenomena of shear stress deposits. And so if we look at this, we have analyzed, various different deposits on a bearing surface. One of the interesting things that we've noticed is that on EP turbine oils. So basically, turbine oils that have a little bit of phosphorus to provide gear protection for any turbo sets that have integrated gearboxes. EP additive, as I'm sure many of you are aware, this is a temperature activated chemistry. So we need a pretty high temperature. And in fact, EP additives are really, designed for gear teeth, and when the gear teeth are touching, the first time the gear teeth touches, it creates a very very high temperature, activates that EP additive, and creates that nice film to prevent further metal to metal touching. However, we need a really high temperature to cause this reaction, and typically we're looking at temperatures over 200 degrees C before that EP additive is activated. And so how are we actually finding varnish or phosphorus derived deposits that are here in the, this would be kind of the hottest spot on the bearing. A lot of temperature at 200 degrees, Babbitt is melting at 132 degrees. That's where we start to see Babbitt creep. 200 degrees is way higher than that. No one is going to be running with a 200-degree temperature bearing in their system. They will shut down way, way, way before then, or they will trip off before then. But actually, what is occurring is not actually on the metal surface, but the oil film. We're creating it can only be a 20 micron film, but within that 20 micron film, we're seeing really, really, really high temperatures that are causing the formation of these degradation products and immediate formation in this isolated high temperature localized regime. So I thought that was pretty interesting that we have identified that there are some really high temperatures that these oils are sometimes seeing, but it creates essentially what we see as varnish-derived temperature excursions. So we see these sawtooth type diagrams. And this is what happens over a 500-day spike, where you see these sawtooth temperatures that are continually increasing in frequency and in amplitude. And so first case study I'll show you is actually from the graph that I just showed you when we added solvents to the system. It essentially stopped the bearing temperature spikes. It was a significant drop in bearing temperature, and then it's basically this is looking at a year and a half after, and it basically flatlined the temperature. So solubility enhancer can in fact be used in some cases to provide a good troubleshooting for this shear stress deposits and these localized deposits that we see. Another troubleshooting thing that we sometimes see is rapid filter plugging. So this was in a PAO that was used in a hydrogen screw compressor. the the turbine always changed every year, so that's probably could have expected longer life on this. However, the biggest pain point for the customer is that they were changing the filters every week, and that was a pain in the butt. So they essentially had a solvencer to this. I did keep the MPC down in a very down to a low level. It did prevent annual oil changes, but the big thing is the filter plugging stopped. So that was really the big benefit here. You stopped this kind of premature. The filters were not plugging because of dirt. They were prematurely sliming over with deposits, and by keeping all of those in solution, we actually allowed the filters to do its job to actually just filter degradation or contaminants rather than slime over with degradation products. And then one other troubleshooting, we had heat exchanger bundle that customer, we don't recommend people do this, but they actually put this dirty heat exchanger bundle back into the system, added solvencer to this, and then 30 days later, this is not shining clean metal. This is not looking brand new, but it is significantly cleaner, and you can in fact see the cleaning action after 30 days of using solvencer. And then the final thing, I just want to take a step for a moment outside of the world of rotating equipment and just touch on for a moment heat transfer systems. Heat transfer systems are really challenging because you're dealing with an incredible amount of contaminants, and they're circulating at such a high temperature, 300 degrees and above. You may not, there's no filter in the world that can withstand being filtered at such a high temperature. No filter that has any kind of resin or glue that's holding it together, which it'll melt the glue and dismantle the any type of normal filter. So it is challenging to deal with contaminants in these systems. Also, we find that heat transfer systems, they're fairly abused. They're not maintained nearly to the same level as say your precious rotating equipment. But this was a case where they had pretty significant temperature or thermal balance issues. Within a few weeks of adding mobile solvencer, you can actually see what it looks like there. It's pretty boring to look at. It just looks like water. But after a few weeks of adding this, it restored the thermal balance in a asphalt plant here that was using a heat transfer fluid. All right, so the first iteration of a solubility enhancer that we developed, where we started on in 2009, and then we commercialized in 2010. The Achilles heel to that initial technology is it worked well, but only for only for a period of time. So we told our customers, you should only use this for a maximum of 6 months, and because long term, that molecule would start to degrade and cause deposits. And the last thing you want to do is to add something to the fluid that could cause some, long-term implications. But we had a lot of customers that would start using the product and then say, oh, we've had to delay our outage. And so we're going to have to use this for more than a year or more than 6 months, which always made us really, really nervous. So we've continued to develop and work on new chemistries. So the mobile solvencer now is something that we feel very comfortable with that could be used long term. And I'll share with you some if we do use this long term, how this can be used as a tool to help extend the life of rotating equipment oil. Typically, we would use this at a 3% treat rate. So the first thing is, if you add this into a system, if you're measuring the varnish potential of the fluid, you see a high MPC. You typically, when you add mobile solvents into the fluid, a short while later, within a matter of a day or two, you typically see single-digit MPC values. So that it works really fast. But how long does it work for? So I think that is the big question. So we do have some long-term field tests, One of the challenges I always find with field tests, um, there's two aspects of this. First, you can only learn so much in the lab. At some point, you need to actually take chemistry out in the field and see actually how it performs in the equipment. So that's the first thing. So field tests, you can never supplement field tests with lab tests. The challenge that I find is that you never encounter the exact same parameters. The gas turbine may be operated in a different location under different thermal loads at a different duty cycle. It could be base loaded versus cycling. So it's really hard to duplicate field trials. So one of the nice things is by doing this laboratory work, you can really get a very a precise way of kind of um, duplicating tests. So we developed many years ago a test that we refer to as a turbine oil performance prediction test. And it's the same stress parameters. If you're familiar with the dry toast test, same stress parameters as that, 120 degrees C. We stress the oil for 12 weeks. We take samples at weeks 3, 6, 9, and then 12, and see. And basically what we're doing, as opposed to the dry toast test, we're actually performing all of the normal tests that you would do, in your normal condition monitoring program. So viscosity and acid number, RPVOT, the membrane patch colorimetry test, ruler test, and we're actually seeing, based on those tests, how do these different oils degrade? And so here is a typical how a typical oil would degrade. You would see the MPC over time would increase. You can see from week 3, week 6, week 9, week 12, we see a continual increase in the MPC value. We see the phenols degrade quick. And that is quite common. Phenols are essentially sacrificing themselves to help the amine antioxidants survive and perform their job. Really, the life and performance of a turbine oil is largely dictated by the performance of the amine antioxidants. So you see the phenols deplete pretty quickly, and then you also see fairly consistent results between the amine and the RPVOT. They're kind of tracking down together. So this is a typical turbine oil and what we would see. So we have tested over the years many different types of turbine oils, and this is an example of 31 commercially available turbine oils. Um, so if you've ever had your oil company say, "Look, not all oils are created equally. Ours is better." I don't know about the ours is better part, but I can definitely say not all turbine oils are created equally. And you don't need to see any other oil analysis data, but just look at the glassware at the end of the test, and you can see between 1 and between 31, there's a pretty big difference. And if I was using a gas turbine, in a fairly thermally stressful environment, I'd be pretty uncomfortable using any of the formulations that are kind of in this top row here. But one other thing, not all turbine oils are created equally. However, we have seen a tremendous improvement in turbine oils over the last 20 years. So the latest generation turbine oils are performing much better than the previous generation. So that's something that I think is very encouraging to see. Some of the newer turbine oils really perform phenomenally well, and an order of magnitude certainly over any of the Group 1 base stocks we saw years ago. But a lot of people will say, well, synthetic, you move to a synthetic oil. In fact, ironically, the best performing turbine oil that we've ever tested is a Group 2, and the worst is probably a Group 3, but Group 2 is followed shortly after that. The Group 1 oils do not do well in this test at all, and this is again going back to you know pointing all of these varnish issues to Group 2 oils is really misplaced blame. Group 1 oils will not do anywhere close to the same level. Once a Group 1 oil after 3 weeks, you'll already start to see acid number increase and viscosity changes. You'll start to see viscosity increase. You'll never see that in Group 2 and Group 3s. So in general, I would say Group 1s, it's probably suitable that we have retired most of the Group 1s. And again, that is not the source of the varnish issues that we see in the world today. Um, so that being said, that is a long introduction to say this is one of the tests that we use to assess, in a controlled environment, what happens if you use a mobile solvencer into an oil, and what kind of impact will that have? So this is a new oil. And again, we're just to make things visual and simple. We're just looking at the MPC patch and the glassware. Yes, there's a lot of other tests as well, and we have a lot of other test data. But just to look at from a deposit perspective, this particular formulation after 12 weeks, lots of stains on the glassware and elevated MPC. Same oil with 3% mobile solvencer after 12 weeks, no stains in the glassware, nice low MPC value. And we've also assessed, other oil solubility, oil solubility or solubility enhancers as well. The big takeaway that I would say is before you add anything to your system, make sure appropriate long-term tests have been done. There are other solubility enhancers in the market. Make sure that there are suitable long-term tests done if you want to use other solubility enhancers more than for a few weeks. So, in fact, this is with mobile solvencer in the bath for 18 weeks. Still, after 18 weeks, we had single-digit MPC values. And in this case, mostly in this particular formulation, most of the antioxidants had been depleted, and it still did a pretty good job of maintaining low deposits in the catalyst coil and glassware as well. So then we always get the question, well, so that's an ideal case. You're dealing with new oil. You're adding this to new oil, and in a perfect world, what happens if you actually add this to an in-service oil? So we try to also emulate this in a long-term test as well. We basically, this particular formulation, we beat this oil up for 12 weeks. After 12 weeks, we added a mobile solvencer to the formulation, and then stressed it again. We 13, 14, 16, week 18, and it still maintains low MPC values compared to a competitor, which really actually it seemed like it worked for a couple of weeks, and then so I would just be again cautious about using competitive fluids a longer term for this. And then also, if you look at the glassware, even we're adding mobile solvencer to basically dirty glassware, and it's slowly remove some of these deposits in the glassware over the course of an extra 6 weeks in the bath. So these are some test results that gave us some maybe some confidence that in fact this could be used long term. And this is actually a real life case in the field where this oil was, I would say, was being changed prematurely. It was basically being changed every 3 years because I'm sorry, I am not showing on the y-axis here. The y-axis here is the MPC value. They were changing the oil prematurely because of elevated MPC value. After adding a solvencer technology, this oil now since 2017 is still running. It's in fact very close to my office right now. So I visit this plant fairly regularly. We still have single-digit MPC values. And again, it's not actually improving the life of the antioxidants. It's not making the antioxidants last longer. It's just maintaining low varnish levels in the oil. So this is a kind of long-term case study that we have on this. So are there limitations? Absolutely. So sometimes it sounds like, look, this this sounds like it's too good to be true. You just add this in and don't have to worry about varnish anymore. That is in fact not the case. We still recommend following ASTM 4378 and doing all of the normal tests that you would do. You should still be doing MPC tests, and essentially you should still be changing the oil or taking some kind of action when the antioxidants get down to 25%. So at some point, you can imagine that the oil could become saturated, even with the solubility enhancer in it. The oil could become saturated and then start producing deposits. So it's still always important to treat or to monitor the fluid after you add this in, and also it doesn't work on inorganic deposits. It's dissolving things. That's the action. So if you have a bunch of even depleted ZDDP additives or inorganic deposits that are in the fluid, it's not going to dissolve those. If you have a bunch of dirt in there, it's not going to dissolve the dirt. So just be aware of that. And also, do you think it's going to work on an oil with an MPC like this? This is the most insane MPC picture I've ever seen. That is actually an MPC patch and a lot of deposits. And thankfully, this is not in a piece of rotating equipment. But the answer I would say would be no. It would not work in this case. So anyway, that's high level overview. And just to conclude, I would say that today, I think we understand varnish a fair bit better than we did in the past. We have testing methodologies that can predict the formation of varnish. We have predictive tools that can benchmark different formulations and predict how different turbine oils are actually going to perform in the field. And we're understanding even things like shear stress deposits. We're starting. It's still a ways to go to fully understand that, but we're starting to understand under what conditions we're seeing these very, very, very high localized temperatures and bearings. So there's still more to learn, but it's absolutely possible to have a varnish-free operation today. The use of solubility enhancers, back in the day, it was always frowned upon to ever add anything to an in-service oil. And so this is, but we're seeing this is being used more and more and more today. By not just Mobil, but other oil companies as well. And solubility enhancers can, in fact, be a really good tool for conversion enablers to when you're doing an oil change to help decontaminate an oil system without having to use an incompatible detergent-based cleaning system that is essentially incompatible with the oil. It helps troubleshoot varnish problems. It can be used to extend oil life. And again, just a final warning that before using solubility enhancers or adding anything to an in-service oil, make sure suitable testing has been performed. So thank you very much, and I would love to answer any questions that you may have.
Okay, thank you very much for your presentation. Do you want to monitor the chat yourself, or you want me to read the questions to you? We have a lot of good questions in the chat.
Oh, fantastic! So
and
I just stopped sharing my screen so I could actually see the questions.
Okay.
So I can go through and if I need to show my screen here, then I can.
Well, I can read them to you. The first question is by Peter. He says, "What's the hydrogen seal failure?"
Okay. Thank you, Peter. That's a great question. So so oil is used as a medium in hydrogen seals, and it's a fairly low flow rate in a low clearance zone. And one of the challenges is if you start to get deposits in the hydrogen seal, then the oil flow becomes a little bit less, the temperature becomes a little bit more. So a tiny bit of deposits start to be cause a formation of a lot of other deposits. And then you'll actually have very, very high temperatures that can actually cause the metal to deform on seals. I have lots of pictures that I could share with you on this, but that's a great question, Peter.
Okay, so the next question by Ahmed is, what size molecule is when the varnish issue is harmful? I mean microns?
Yeah, that's a great question. So varnish. So first, I just want to separate varnish a little bit from oil degradation products. So yeah, varnish is actually the definition of varnish or oil derived deposits. So there's actually no varnish in the oil. What's in the oil degradation products, and then they come out of the oil and form varnish. But the tricky thing about varnish is that it's soluble in the oil. So in terms of a micron size, it is literally it's dissolved in the oil, so it's like measuring the micron of dissolved sugar in your coffee. It's not actually a particle that you can dissolve, it's part of the oil. But once they start agglomerating together and becoming they can become fairly large in size, so large in fact that it will you can actually see this on a 4 and 6 micron particle count. So if you see a particle count with a very high 4 micron code, and your 14 micron code is low, that is a good sign that you should do some additional testing. So it can become, as large as 4 or even a 6 micron, but once it starts agglomerating to that size, it starts to no longer be soluble in the oil and come out of solution. So there's not a clear answer on that. You want to keep all these degradation products dissolved. When they start agglomerating, at some point you're going to reach that saturation point of the oil, and that's when problems start to happen.
Good. So the next question by Peter is, what happens when the solvency becomes saturated?
Yeah, perfect. Great question, Peter. So yeah, at some point these solvents may not last forever. That's why you need to keep running MPC tests. Once it becomes saturated, you're going to start to see the MPC slowly increase again. So then you can take action. You can change the oil. You can put a varnish mitigation system on. You can add some more mobile solvencer. So there's some other things that you can do as well. But yeah, that's a great question. It's not a silver bullet that can make the oil last forever.
Okay. The next question is, when the deposit is dissolved by the adding of mobile solvencer, what happens if the system is stopped and the oil cools down? Will the deposit resettle down?
Yeah, yeah. So it will theoretically it can, but keep in mind the MPC test. When you're running the MPC test, you're heating the oil up to 65 degrees C for 24 hours, then you're letting it cool for 72 hours. That's to allow all these contaminants to come out of solution. And with mobile solvencer, you'll still see very, very low MPC values. So even at a room temperature for an extended period of time, it's going to keep all of these things in solution. So that's that's a really good that's a good question, but it does a very good job even at room temperature or cooler at maintaining the solubility of these.
And the next question is there a parameter apart from annealing point that can have predict the solvency power of a lubricant?
Yeah, excellent question. So I would say the polarity is just one aspect of solubility. So we use a 3D model to estimate the same 3D model that's used in the water chemistry world, following Hansen parameters, and it's used at polarity is one aspect, hydrogen bonding is another aspect. And the
Okay.
third parameter, I just slipped my mind. So that's it. But essentially, what I want to say is the aniline point is only looking at polarity, and this is only just one perspective. So you can have oil that's extremely polar, say like an OSP, oil soluble PEG can have a very, very low aniline point, or even a PEG can have an aniline point of minus 40, yet it still may not be so good at dissolving some of these chemistries because there's other parameters involved other than just polarity.
Okay, great, thanks. Question by Bruce says, could microdieseling be causing the increased heat?
Yeah, that's a great question. So yeah, under that extreme amount of pressure, if you have air in there, absolutely that could cause microdieseling to happen. In reality, we actually, so I think we have a good understanding of the mechanism for when microdieseling happens. But microdieseling is actually a fairly easy thing to detect whether or not it's actually happening in a system. Over time, a system that has microdieseling, you're going to see the oil will literally start to look, instead of like a nice amber ale color, it's going to start to look like a black stout. It's going to
Mm,
be absolutely black in color. The MPC, you could have an MPC patch that is the color of the night sky. So it will create over time a lot of deposits. And in reality, we the only turbine applications that I see have issues with microdieseling. So some compressor applications we see microdieseling, but the only turbine applications that I see are some hydroelectric applications in the governor system. If you ever pull a turbine oil sample from a hydroelectric dam that is black in color from a governor system, you have microdieseling. But in the vast majority of other turbine applications, is really really rare to see.
okay.
Great question.
This is my question as well. I think when you talk about the heat transfer systems, Peter asked, what's the maximum temperature solvencer can handle?
305 degrees C. Thank you very much. Good question. Yeah,
205. Okay.
305
So
C.
going down, Brian asked if the chemistry oil soluble, is the chemistry oil soluble PAG?
Yeah, so oil soluble PEGs are another chemistry that are often used as solubility enhancers. One of the challenges with OSPs is that over an extended period of time, it can create actually much more deposits that were in the system to begin with. So OSPs, again, they have they're extremely polar, very low aniline point, and they're actually somewhat effective for a short period of time. But I would only consider using OSPs for, it's a maximum of a month or two. And this is, although this is a Group 5 base stock, I will say it's not any kind of common Group 5 base stock that you probably encountered before, not like alkylated naphthalines or OSPs or esters or things like that. So it's a pretty unique chemistry. Great question.
So the next question, when was Solvencer developed? You said 2010 or something like that?
So the first iteration of a solubility enhancer is developed in 2010. We developed mobile solvencer. The solvencer chemistry was developed in 2015, 2016. We were doing lab tests, and our first trial in the field was in 2017. And again, I showed actually a case study of that system that still has a nice low MPC.
Okay. How about the thermal stability or the composition temperature of the product?
Yeah, so that is one of the magical parts of the product. If you actually put this on a burner plate and burned it, it wouldn't leave deposits behind, which is a little bit unique. Pretty much anything, if esters or pegs or anything else, if you throw enough thermal uh, um, stress on these fluids, they will degrade and form lots of deposits. But we don't have that with it doesn't produce any. If you burn mobile solvents or it doesn't produce deposits? Great question.
Okay. So the next question, varnish can be found in elemental analysis like EDX or XRF or normal analysis. Which
Yeah,
one?
that's a great question. So in the world of rotating equipment, with turbine oils, no, these are not effective tests. Because the degradation products are decomposed additives or decomposed hydrocarbon molecules, and basically there's no metal content in varnish. However, if you look at, say, varnish deposits in hydraulic systems, you may find various different phosphates, zinc. You may find you can identify sulfur. So yeah, you can absolutely use XRF or SEM-EDX for looking at deposits that are not, say, in non-turbine oil systems. Great question.
Okay, so next question before I read it. ESD means electrostatic discharge. So here's the question. What are your thoughts on the fact that group 2 and group 3 oils respectively tend to have significantly lower conductivity, we significantly increase the risk of EDS? And do you consider EDS to be a major contributor to the formation of varnish?
Fantastic. So I have a whole range of different videos of electrostatic spark discharge. They are very dramatic. Whenever end users see them, they're like, "Oh my, I can't believe I have sparks actually happening in my oil." Um, I would say I used to think that this was or in fact, this could have been a more leading cause of varnish years ago. For the most part, a lot of people filter technologies have improved. There are a lot of filters that are using dissipative medias that don't allow the accumulation of static electricity. So I would say today that we are ESD is a less contributor to oil degradation than perhaps we've seen in the past. But the point that group 2 and group 3s have lower conductivity, that's absolutely true. We see a lot of oils have less than 1 picosiemens per meter conductivity ratings now, and the lower the conductivity, the higher the chance of ESD. So I think those are there's absolutely a correlation between low conductivity oils and ESD. But again, I don't think ESD is as big of a contributor as it to varnish as it has been in the past.
So Rafael says, hello, what kind of test I should do to check the compatibility with my oil?
Great question. So ASTM is developed to test D7155 that's specifically used to test the compatibility of turbine oils. This was developed due to in a large hydroelectric dam in the United States. We incompatible oil was added to a system, and it caused a major outage at this hydroelectric dam, and then that started the process and within ASTM to develop a testing methodology. But if you look at D7155, that would be the first thing I would look at. And the other thing I would say is that in incompatibilities, the thing that fails first is really it's not common to mix two oils and then see a flocculant and see the oil suddenly turn cloudy. That is really significantly incompatible. However, if you mix two oils together and you see demulsibility go, or air release suddenly go up, or the foam levels start to increase, those are the first early signs of incompatibility. So those are the key tests that I would really look at.
Perfect. So varnish is a magnetic or non-magnetic particles when they agglomerate together, when they stick together. Is this have effect on PQI, or could corrosion like oxide form? Whether we can find it in the analytical ferrography?
Yeah.
I hope I read
Varnish
it
is
correct.
non-magnetic. Yeah, so non-magnetic. In analytical photography, you can see some nice golden striations that may suggest deposits. So a lot of times you'll see comments about varnish or oil degradation products on the analytical slide, but for the most part, those would not be a successful tests at identifying varnish.
Okay. So the next question is, if turbine oil have high conductivity and transformer or fluids have high insulation properties, both have high varnish. So varnish will form in conductivity or non-conductivity fluid.
I would say the properties of which, when varnish forms, are not necessarily related to the conductivity of the oil, but both, transformer oils and turbine oils are extremely nonpolar, and so they could be prone, arcing and things that happen in transformers. There's a correlation between that and ESD that we just talked about in turbine oils. But generally, I would say there's not really an influence on deposit formation and that mechanism on the conductivity of the oil.
Okay. And the question is, microbial infection will lead to varnish?
Yes. Yeah, absolutely. So,
Does.
um, I guess we refer to varnish as an oil derived deposit, and bugs that are eating the oil. I don't know if that's internally generated or not. Probably not. So we
Mm.
would probably call that something else other than varnish. But it's not so. Luckily, it's not so common to have uh, bugs growing in oil. But if you get a sample of oil that smells like dirty socks, and you're dealing dirty wool socks that are wet and nasty, that is typically what we see microbial growth in turbine oils. It starts to give that odor to an oil, and again, we typically would see that in old steam turbine systems that would have stagnant pockets of water. Not so much in any modern equipment today.
Good.
Great question.
I think you answered the next question. Richard asks us, further to your last response, when there is a static discharge in oil reservoir, often seen in high velocity circulating system, then he says, you must be seeing my typing. Thanks for the last response. So it seems that he had a question that you already responded.
Okay.
We have Ahmed. Ahmed, you raise your hand from the beginning of the Q&A. Please unmute and ask your question if you still have the question. Or anybody else who wants to unmute and ask the question, please go ahead. We have a couple of more minutes to wrap up
Hi,
the meeting.
hi, Sabah. Thanks a lot for giving me the opportunity. I'm a great fan of Greg. I along with he along with Sania Mathura, whom I call the Varnish Queen. They are the excellent authors of book. What's it called? Turbo Machinery, Cholesterol, and I follow them very closely. I'm firstly thank you answer my question. Secondly, you mentioned in your note that this experiment was first done. Technology was introduced in Canada. So where I am from Canada,
Uh,
in your
the
write
tech
up, yeah, the solvencer technology was first
Do you
introduced
have
in.
any test site in Canada, Greg?
Yeah, we do. We have some excellent case studies in in the tar sands, several in Fort Saskatchewan and throughout Alberta, and also in some in southern Ontario. So yeah, so I can share some data with you. The technology was developed in the U.S., but me being fellow Canadian, I love seeing the technology being used north of the border. So thank you very much for your comments. I appreciate that. So,
Thank you, Greg, and thank you, Saba. Okay.
Thank you. Okay, Greg, any other things that you want to add for this? Before we have a question, but you go ahead and then I read the question to you.
it looks like Raj just answered or asked a question from Singapore.
Yeah.
Um, it is just after midnight in Singapore, Raj. I don't know what you're still doing awake. So heat transfer oils have high cracking and many times due to overheating and hot spots. No test for varnish stipulated by the oil markers. We found thermal cracking. We found CCR and asphaltenes. Is this varnish? So I would say, it under the definition of varnish as an oil-derived deposit, absolutely. The deposits that we see in heat transfer systems would be considered varnish. But and also just to share with you, that is actually from a heat transfer system. So that is a very, very nasty looking patch. There is no MPC that you can get from that, but so yeah, heat transfer systems absolutely have very high varnish potentials, and CCR is a great test to help identify deposits in those systems. Thank you,
Perfect.
Raj, for your very
Thank
late
you
night
very
question.
much. Thanks. Solongo, do you have anything to add before we wrap up the meeting?
No, I don't. I just want to say thank you again to Greg for taking time out of your day to come talk to us. We appreciate it.
Of
Okay.
course.
Okay, Greg, thank you from ST Toronto section to you and the great presentation that you did. I thank everybody for their participation and the questions. As I said, this video will was recorded, and then I will put it up into the YouTube channel and the company website. Thank you, Greg, and that would be it. Thank you, and have a great day.
Thanks
Bye
so
now.
much.
Thanks, everyone.
Bye-bye.
Bye.
Thanks.
Bye
Bye.
bye. Thank you.
Bye. Bye. Thank you.